There we go. The recording is on. So this is the truth table that we ended up last time. This one is not organized the same way as the one that I talked about on Tuesday, but it's basically the same truth table. And so this is a continuation of where we left off last time. So as a reminder, it is really important to kind of go through the material um, from the previous class before we get started in the next class. So right here, I'm describing the NAND gate. So if W is the output and X and Y are the inputs, then W is the logical NOT of the conjunction between the two input pins. So that's also what we talked about um, on Tuesday. Um, in terms of symbols, this is the mathematical symbol of negation or not. This is the mathematical notation of and. So for people who are used to math symbols, this is the notation which expresses exactly the same thing as this particular, C++ notation. In computer engineering, it is fairly common that people use an overbar to mean negation, and people also use a dot or multiplication to mean conjunction. So that's just your convention, used by different people in industry, in mathematics, and also sometimes people don't even put a dot. So when you see something that looks like multiplication, it actually means conjunction. Okay, so we are only talking about a bunch of notations for what we need to express. But at the very end, we are just still looking at NAND. So the operator is known as, it looks like an up arrow. So when we say X up arrow X, we are basically saying X NAND X. Or we are looking at the negation of X and X, which is not surprisingly just the negation of X. So are we okay with that claim? Where the mouse pointer is, the negation of X, the logical NOT of X is really just X NAND X. So are we good with that? Okay. So let's just say that, you're not sure whether, tech is trying to trick you or not. Because one of the comments that I got on ratemyprofessors.com was a complaint that I try to trick people in the exams. Okay. Well, I guess it's too late for you guys. You're enrolled in this class, and there are no other classes you can go anymore. I'm just kidding. But just in case you want to verify this, okay? So how can you validate this particular, equality over here? So do you know enough skills to just double check and make sure that the negation of x is actually x NAND x? How would you go about doing that? Yes. Oh, okay. Does anyone want to give it a try? All right. Well, let's try to give it a try here. Okay. I'm going to use a text editor and we'll go ahead and illustrate it. So accessories, mouse pad. There we go. All right. New. There we go. All right. So basically what we're asking is the logical knot of x. Is it really the same thing as x NAND x? This is what we are asking. Okay. So now the first thing we need to do is to expand NAND so that we understand that, oh, okay, if we just need to use the usual operators in C++, that becomes this. Okay. So once we have this, we can use a truth table. So the truth table is going to have x as one column, the negation of x as one column, and then we have the negation of x and x as another column. Since we only have one Boolean variable, it can only be false or true. Let me turn off the line number because I think it's actually making things worse. There we go. So if x is false, not x is going to be true. If x is true, not x is going to be false. And now we move on to the last column. If x is false, what is false and false? False. What is not false? It is true. All right. So we arrive to this conclusion. And then on the on the second row, x is true. So we have true and true, which is true. Not true is false again. So we can observe how the second column and the third column gives you exactly the same value for every single row on in this particular truth table. So that means those two Boolean expressions are equivalent. Does that make sense? Do we understand how this truth table is settling and proving once and for all that not x is the same thing as x NAND x? Okay, so I see some nods. Okay, excellent. So now we're going to move on. Okay, so we are moving on to what about just regular AND? So this is my claim. My claim is x and y is the same thing as x NAND y, the whole thing, NAND x NAND y, the whole thing. Okay, so that looks kind of ew, right? So once again, the question is, when you look at something like this, do you just kind of memorize and go like, well, since text says this, it has to be true, or do you try your best to validate the claim using things that you have learned already? So the first question is, have you learned the tools and the concepts, basically what you need in order to prove that x and y is indeed x NAND y, the whole thing, NAND x NAND y. What do you think? Have you learned enough to do this on your own? Okay, it might be slightly tedious. Okay, you might go like, ugh, this looks tedious to me. It is a little bit tedious. Okay, but you should be able to do it. Okay, so I'm going to illustrate again, how you can double check and make sure that I'm telling you the actual truth. So once again, this time what we're trying to prove is in C++ notation is x and y is the same thing as x NAND y, the whole thing, NAND x NAND y, because I cannot really put in the mathematical symbols inside the text editor, so I'm going to have to spell out NAND as a word. All right, so what are you going to do? This is my claim. If this is a question in an exam, it actually counts 2 points that you need to pass this class. What are you going to do to prove this? The clue is right above that question. Okay? You use a truth table. So the question is, how do you set up that truth table? Well, this time we have two independent Boolean variables. So x and y are called your two independent Boolean variables, which means when x is false, y can be false. When x is false, y can be true. When x is true, y can be false. When x is true, y can also be true. Does that make sense that I have now enumerated all four possible cases when x and y each can only be false or true? Does that make sense? Okay, all right. So what we do next is we look at x and y. Okay, so the next column is just x and y. And we go like, okay, if they're both false, the and is going to be false. If at least one is false, the and is still false. And when both are true, then the and is going to be true. Does that make sense? All right, cool. So now we look at NAND. Okay, so we now look at x NAND y. Well, x NAND y is the negation of x and y, which means we just flip all the zeros and ones of the row of the column immediately to the left-hand side of the one that I'm working on. Does that make sense? Okay. So now we ask, what is x NAND y NAND x NAND y? So now we ask, what is X NAND Y NAND X NAND Y. Okay, let's see. On the first row, X NAND Y is true, so that means we have true, true over here. This is a negated AND, so we have to perform the AND first and then negate it. True and true is true, but when you negate it, it becomes false. Okay, very good. And the second row is kind of the same deal. We still have, basically true NAND true, which is false. This is also the same thing. This is the only row when we have false NAND false, which means you first compute false and false, which is false, and then you perform the negation. Not false is true, so we put a 1 here. So do you notice that the second column, this one here, is actually exactly the same as the fifth column, which is this one here? Well, then we have the definitive proof that the equality actually holds, because for every possible way for x and y to have values, the expression of x conjunction with y is actually the same thing as x NAND y, the whole thing NAND x NAND y. So this is why truth tables are particularly useful, because you can actually use it to prove two expressions being exactly the same. Are we okay so far? Okay. So what is the significance of all this stuff here? It means if I have a way to implement a NAND gate, okay, which is a hardware version of an operator, I can now use that particular gate or that circuit to perform just regular negation, also to perform regular conjunction. So what is missing? What about OR, right? What about disjunction? So that's going to be the next item, but I am going to leave it up to you to do the proof. So X or Y, okay, so the V-like symbol is disjunction in math, which is the same thing as a double bar, which is the C++ notation of logical OR. So I make this claim that X or Y is ultimately the same thing as X NAND X NAND Y NAND Y. Now, the in-between steps, if you have taken CISP 440, you should recognize, oh, Tech is using that little trick called De Morgan's Law. But in this class, you don't have to learn De Morgan's Law just yet, okay? So you don't have to worry about the derivation, but instead, I would challenge you guys to actually make that same truth table, but this time to prove that X or Y is the same thing as X NAND X, the whole thing, NAND Y NAND Y, the whole thing. In other words, I will leave it up to you to make your own truth table to establish the equality from here all the way back to here. It is not going to be graded, which means you can basically safely not do what I recommend. It won't impact your grade right away, but it is a useful exercise, which means if you do it, it will help you understand the concepts a little bit better. Okay? But some people intrinsically already intuitively understand all these concepts and they don't have to go through the exercise. So you kind of have to gauge for yourself, whether you want to follow my advice, okay, and do the exercise that I recommend or not. All right. But what I have also illustrated is when you are reading the material, you can actually quote unquote generate your own little quiz. Okay. You look at a statement, okay, tag claims, blah, 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 but without any proof. Okay. So you have to ask yourself, have I learned enough material to prove that statement on my own? Okay. You're basically looking for more opportunities to practice problem solving and critical thinking. So why would anyone want extra opportunities to do extra work for no points whatsoever? You'll be better prepared for. Okay, that's not wrong. Okay, you'll be better prepared for the exams and the assessment for this class. But most people, I mean, remember, 37.5% is all you need to pass this class with a C, right? So if all that is going to help is to pass this class, that sounds like a lot of work to me. Okay, so why else would anyone want to find additional opportunities to practice critical thinking and problem solving? Hmm? Conditioning for, okay, but that's circular reasoning because you're telling me that you want to practice problem solving because then you know how to do problem solving. A Yes, to get a job and keep it. Okay, because the key is not just to get a job, but to thrive. Okay, to be successful and be happy that when you go to work. Okay, it's not nice when you have to go drag your feet to work every single day. That would not be good. Is that making any sense? So why do you think, okay, so we're pushing this argument a little bit further, right? So why do you think critical thinking and problem solving are the skills that you need in order to first land a job and two to keep that job? I mean, tech, back in your era, okay, which is like decades ago, that may be the case because you did not have AI, nor the internet. But now that we have the internet and all the GPTs, why do I need to learn how to problem solve and do critical thinking? What is the answer to that question? Okay, nobody seems to be either want to answer the question or know the answer but does not want to disclose the answer. So I'll go ahead and disclose the answer. Okay, so think of it in the opposite way. Okay, think of it in the opposite way. Let's assume AI can actually do all the critical thinking and problem solving that the person can do. Okay, that's the assumption. That's the hypothesis. Why would anyone want to hire you then? If AI can do all the work that you can do, why would any company hire people? And if that is the case, okay, if the companies do not need to hire anyone with a computer science degree, then the next question is it will hurt even more, which is why are you here? So we can only assume that there are certain things that people can do that AI cannot do. Okay? Because without that assumption, it is pointless to pursue a computer science degree. So, assuming that is the case, then the next question is what kind of skill set, what kind of stuff people can do but AI cannot do? It's problem solving and critical thinking. So, that's why I want you guys to get the extra opportunities to practice that. Is that making any sense? So, that is really important because we are reaching kind of close to the bottom of this entire module. So I'm going to show you certain things that relate back to what I just said. So what is left here is really just a very brief description of how numbers and values are represented, but that the next module will handle this in a much better way. So we are basically at the end of this particular reading module. At the very, very end, okay, if you go all the way to the bottom, there are a few hyperlinks. The first hyperlink is just a link to the Creative Commons license, which tells you what you can and cannot legally do with the content that you're looking here. Okay, so the Creative Commons attribution dash non-commercial dash share alike, license allows you to use this content any way, pretty much any way you want. Okay, except for a few things. You cannot, kind of copy and paste this into some other place without attributing. Okay, so that means you have to attribute that the original version of that content was written by TAC. Okay, the second one is non-commercial, which means you cannot use this content in a published for-profit kind of book. Okay, share alike means this license is contagious. Any content that is based on this particular content here, it also needs to be using exactly the same copyright notice. So that's what the licensing part means. The second link allows those people who notice my you know grammatical mistakes or spelling mistakes and whatnot and go like, I cannot stand this, I have to fix it. So if you have a GitHub account, if you click on the second link here, it will bring you to a page where you can make some changes. You can suggest a change to the actual content here, and then you can file what your GitHub calls a pull request. The pull request will get to me. I get to review what you're suggesting to change. And if I go like, oh, this is a great change, okay, you just fixed some of my grammatical mistakes or spelling mistakes, or you're adding a section that better explains the concept, I can click one button and your contribution will now be incorporated into the source document. Okay. The next link is create an issue or participate in a discussion. Okay, so that's for people who want to just, okay, I just want to talk about this content. Okay, but not necessarily knowing how to make the changes. So that's for that purpose. The last two links are particularly useful. Okay, so I'm going to illustrate what they can do or what you can do with them. So the second to the last one is for viewing the source document. So it will bring you to GitHub. If you have, even if you don't have a GitHub account, it will still land on a page like this, where you can download the entire source document. So you can click on that link here, and I would download it with the name of the module, which is 0281, like that. Just press the enter key. And then what you can do now that you have the source file, which is in the format called Markdown, there are a few things you can do. If you are curious about, how the original source document looks like, you can just open it with Notepad because it's really just plain text file. But there are more things, more stuff you can do with it. So what you can do is you can go to Gemini, okay? So I hope you already know that every student at a community college in California already has a paid subscription to Gemini. Did you guys know that? Okay, some people know. All right. So what can you do with Gemini? Okay, a lot of things. Okay, and I can just kind of flat out. I know other professors will hate me for saying this, but I'm gonna say it. You can do all your homework already. Okay, at a 2-year community college and possibly at a 4-year university, Gemini can do all your homework, including all the programming homework assignments. It doesn't matter. If it's 400, it can do it. If it's 430, it can do it. Okay, so that's not what I'm suggesting you should use it for. Okay, because that defeats the whole purpose of learning how to think critically and how to solve problems, right? So what you can do in this case is to turn it into your kind of like a TA, but it's your own TA. So what I'm going to do is to click this symbol here, upload the file that I just downloaded. And most LLMs or large language models or GPTs, they natively understand Markdown. And that's the reason why I downloaded it as a Markdown file instead of an HTML. Now, HTML may work too, okay, but Markdown is much more native to most large language models. So now, in the prompt, you can do a lot of things, okay? For instance, you can do something like um, give me a quiz to test my knowledge, problem solving skills, and critical thinking skills. related to the uploaded document that describes um, the NAND gate and related transistor circuitry. All right, and of course, this is supposed to be hyphenated, and NAND has to be capitalized. Okay, fine. All right, and that's doesn't seem like a very difficult problem to come up with, right? So the question is, I actually have not tried this. So we'll go ahead and see what kind of output or what kind of response is coming back from Gemini. I did this with my other class, with my 440 class yesterday. It was actually quite impressive. Okay, it generated kind of like a short quiz, multiple choice and all that. And there are people on this campus who oppose to this approach of doing things because I'm probably, evaporating a few bottles of drinking water right there. All right, so we have a quiz. Do you guys want to do it? Let's do it, right? Just to check out the quality of the output. It's not quite done. You can see that it's still generating more questions. So according to the module, what is a primary operational difference between a vacuum tube and a transistor that contributes to the transistor's superior efficiency? We didn't actually talk about that, even though it was in the notes. So I'm not going to hold you guys accountable to be able to answer this question because I didn't talk about it. So, transistor. Okay, transistor require heating element. No, that's not the case. They do not require heating element because they don't rely on electrons flying through a vacuum. That would be the answer. So that's the reason why vacuum tube based computers generate a lot of heat. Because in order for vacuum tubes to work, it first of all, the inside has to be a vacuum, and two, it needs a heating element in order to pre-excite the electrons so they're ready to jump from the anode to the cathode. Okay, but I didn't talk about it. It's okay. Okay, I'm not holding you guys accountable for this one. All right, in the context of the AND transistor described in the text, what is the relationship between the gate voltage and the state of the valve? Okay, so the gate voltage must oscillate to allow flow. I don't think that is the case. A high voltage at the gate turns the valve on, allows flow. The gate voltage has no effect on the flow, it only controls the direction. No. A low voltage so this question is definitely not well formed because there are two different kinds of transistors. So it depends on whether we are talking about an N-type or a P-type transistor. So when you read this question, you go like, well, but the question is not giving me enough information. That means, yep, you're understanding the concepts, okay? Because it depends on what type of transistor we are working with. So I'm curious as to what kind of hint it's going to give. Think about the intuitive type of transistor where a positive or high signal activates the device. I'm guessing this is the what it thinks is the right answer. Ah, now it tells me for an N transistor. Hmm? Say again? Oh, it did say. I didn't read my question carefully. That wouldn't be the first time. Oh, yep, it did say it's an N transistor. As I said, usually I would be a B student in my own class because I'm careless. All right. The module describes a T-N2P circuit comprising two P transistors Q1, Q2, and two N transistors Q3, Q4, which are exactly the way that I named the transistors on Tuesday. How are these transistors arranged to form the circuit? Ooh, so it's textually describing the connection of the transistors. Q1 and Q2 are in parallel to the high voltage Q3, Q4 in series connected to ground. Yep, that's the answer. But since I didn't talk about what is in parallel and what is in series in a electrical circuit, so you may or may not know how to answer this question. Okay, it depends on whether you have taken the physics class or an electronic technology class that talks about, what is connecting something in series and connecting something in parallel. All right, moving on. Next question. In the 2p, 2n2p circuit analyzed, what is the state of the transistors when input X is 1 and input Y is 0? Ooh, that is a little bit harder because now it depends on um, which one is Q1 and which one is Q2. So you have to go back to the notes to look at the actual connectivity. And since I cannot really remember, so I'm not gonna blindly guess, okay? Because we know the output is going to be what? Well, it doesn't ask about the output, but we know that in this configuration, one of Q1, Q2 is on, the other one is off. One of Q3, Q4 is on, and the other one is off. So I can rule out A as a possibility. I can rule out B as a possibility. C is possible depending on how the connectivity of X and Y to the gate of the transistors, and D is also possible. So both of these are possible, and the only way to differentiate and come up with the correct answer is to actually look at the circuitry in the module, okay, and use that as a hint. So do you want me to actually look it up so that I can figure out the correct answer? Or do you think you guys can do it? All right, so let's do that. Okay, so I'm gonna go check the notes. So the specific question is X is 1, okay? X is 1, Y is 0. So we just have to kind of scroll back up, mm, look at the question. Okay, so this is probably enough for me to answer the question already. So X is high. So if X is high, then Q1 is off, Q2 is on. Okay, so that gives me enough information right away. So we can go back to here. Q1 is off, Q2 is on. So Q1 is off, Q2 is on, Q3 is on, Q4 is off. Right there. There we go. So are you guys following my reasoning? How I look at the diagram and only work out between Q1 and Q2, and that gives me enough information to resolve between C and D as possible answers. So that is problem solving. Okay, you're using hints. Okay, to narrow down to the correct answer as quickly as possible. Okay. All right. Moving on. Next. Based on the transistor states when input X is 1 and input Y is 0, which is the same thing that we just looked at earlier, what is the resulting output voltage of the circuit? Okay, well, that's a really good question because you can do it in many ways. Okay, you can just blindly guess, okay, which is not recommended. Two, you can look up your notes because we talked about all four possibilities in the previous class already. Or three, you can try to work this out on the fly, like right away. So in this case, it's hard for me to emulate the last option because I already know how the circuit works. So in this case, if at least one input is a 1, the output is going to be, oh, I should say it the other way. If at least one input is a 0, then the output is going to be a 1. And since we know one input, which is input Y, is a 0, so the output is guaranteed to be 1 already. But then I have to choose between these two. So between these two, whether the output is high because Q1 is connecting the output to the high voltage source, or C, because Q2 connects the output to the high voltage source. So now we have to go back to the previous question, right? The previous question, we already know that Q1 is off, Q2 is on. So that means Q2 has to be the one that is connecting the output to the high voltage source. So that means the answer to this question is probably C and not B. There we go. So are you guys following my reasoning, the way that I work out these problems? Okay. Because that part, okay, interestingly, is probably more important than the circuitry itself. It's the approach of how to solve a problem. Okay. All right, moving on. I'm quite enjoying this little quiz that the AI is generating. The module asserts that the 2N2P circuit implements a NAND gate. Which of the following truth table behaviors support this claim? The output is 0 only when both inputs are 0. Nope, that's a regular AND gate. The output is a 0 when both inputs are 1s, otherwise it is a 1. Okay, I think that's the answer right there. I didn't even have to look at the other two. Okay, using the NAND operator denoted as the up arrow, what is the logical NOT operator constructed? Well, if you have reasonably good memory, you just kind of still remember all that stuff, you just click on this one. It's done. And next, how can an OR operation be implemented using NAND gate only? Aha, I still remember it's this one. So we can kind of see how this can be helpful. The text mentions the Colossus computer. Now this one is going back to before section 3, so that may or may not be um, um, something that you can remember because we never talked about it. So what does that sound? Okay. Hmm. All right. So it uses early silicon transistor, which were too expensive. Electromechanical, no. Vacuum tubes, bulky, hot, and energy consuming. We never talked about hydraulic valves, so D is off entirely. I think it is the third one. Yep. All right. Last question. Why is computer science described as not being a science regarding the truth of nature? Because it is a study of the implication of artificial rules. It's the last one regarding truth values. That's it. There we go. Yep. Typically, when you look at a certain subject, if it is XYZ science, it is not a science. Is there a science in physics? No. Is there a science in chemistry? No. Is there a science in biology? No. I think you get the point. But there is a science in political science. There's a science in computer science, but neither is actually science. So if computer science is not science, what is it? Which major main category of subject matter does it belong to? I'll give you some options. Science, engineering, math, art. Pick one. It is actually math. It is closest to math. It is related to engineering, but it is definitely not art. And I already told you it's not science. Yep. There you go. So I am hoping this little exercise is convincing you that you can indeed use a GPT or LLM, okay, however you want to call Gemini, to help you in studying in terms of understanding the material and also in terms of training your mind so you can do problem solving and critical thinking. Is that okay? Has anyone ever kind of given you these instructions or demonstrated what AI can help in terms of studying? Okay, you were nodding. So who taught you? Oh, okay. Because he took my class before. Okay, I was hoping somebody else is already doing this too. How about someone other than me? Yeah. Okay. Yep. It depends on how you prompt it. Uh, I'm not really a huge fan of Sam Altman in general, but he did say one thing that is that I think has all the truth. He said one thing, somebody asked him what is the most valuable skill set, in the 21st century, and he said it is knowing what question to ask. Okay, so kind of think about that, when you have time, is knowing what question to ask. Not so much knowing the answer to the question, but knowing how or what to ask. Okay, so that's actually a interesting skill set. Okay, alrighty. So now that we are done with this module, we're going to move on. And we are looking at the time. We got plenty of time. So we are moving on to the next module, which is down here. It is called Values, Numbers, and Bases. So this is our next module. So when you are done reading a module, all you have to do is to kind of sequentially move on to the next one. That will give you kind of like a head start on the next topic. Some people do not need to do this. Some people should do that. Okay, so whether you need to do this or not is entirely dependent on who you are and what method works best for you. Um, so I'm going to spend also burn a little bit of time to talk about that because when you are taking easy classes, you don't need to do it. But when you're taking classes that are more complicated, as you will find out, some of you might need to do this. Okay, so I'll talk about the tale of two computer science people. I'm one, and then one of my friends who probably has an IQ that is 30 points higher than mine. How do I know it? Because he is so smart that I can barely follow what he's talking about. Okay, that's usually the borderline, of about 30 points of IQ. So he's super smart, um, but he's the one who has to read the notes or read the reading material, read the textbook ahead of time, and read it afterwards, and also read his own notes. I'm the person who can go to a class without reading anything ahead of time, take my notes, and then completely ignore the notes that I have taken. So you might wonder, how can that possibly be the case? Because I'm the one who is lower in terms of IQ by 30 points, right? So as it turns out, he has what is the condition? It's the way when people look at something, the ordering will start to kind of jumble up. Dyslexic, right? He's dyslexic, and I'm not. So when you are dyslexic, you have to read slower, and you have to read more often in order to get the sequencing of things right. And that's why he had to read the material ahead of time. He had to take notes, and he had to read his own notes after each class. And also, he cared about his grade a lot more than I do, so that's the other reason. On the other hand, I am fueled or driven by curiosity. If I were to read the notes ahead of time, that would have killed the curiosity. I would go to the class kind of knowing what the professor is going to talk about, and I would not have any curiosity, and then I would get distracted because I have ADHD. So that's why, different people do things differently. But I still have to take notes because if I don't take notes, my mind would not have something to focus on, and then it will start to wander off to things that are not related to the class. Eventually, I would completely miss what the professor is talking about. So I still have to take notes. It's just that I don't usually have to go back to read my own notes. All right. So whether you should take notes or read the material ahead of time or to review the material afterwards, it's all dependent on how your mind works and how your brain is structured. Because dyslexic is not just psychology, it is actually hardwired. Okay, some people's brain is just hardwired so that we call those people dyslexic. Okay, so I will kind of, sprinkle things like this, throughout the class, just so that you understand, what you need to do when you try before you transfer to a 4-year university. Okay, because it's going to be a lot more rigorous. Okay, and it's going to be a lot more expensive after you transfer to a 4-year university. So it's best to perfect your study skills when you're here. All right, so we are going to be talking about base conversion. So before we talk about base conversion, which is a subject matter that some people feel is, oh, that sounds really complicated. It's not complicated at all. So instead of talking about base conversion, I am going to talk about how do you make change for a certain amount of money in US currency. Okay? So does everybody understand the US currency, the denomination? Like we start with a penny, and then we have a nickel, and then we have a dime, then we have a quarter, and then we have a dollar, and then five, and then 10, 20, 100, 50, and then 100, right? So everybody knows all that stuff, okay? In other words, if you absolutely cannot get any job in computer science or anything related, but McDonald's is hiring, do you think you can work at a McDonald's and make change for your customers? I'm pretty sure by the time you graduate, they won't be hiring people either. Have you guys heard about, McDonald's is already turning to robotics to actually make the hamburgers? Okay? If you have not heard about it, it's happening. It's already happening. Anyway, so getting back to making change. So let's just say I'm just picking a number here. So let's just say that I need to make change for $18 and I have to find a certain value that works out for me. So let's just say that it is 25 cents. Okay, $18 and a quarter. Okay, there we go. And I want you to give me a way to give me the worth of $18.25 using the least number of coins and bills. In other words, the easy way to do this is to give me 1,825 pennies, but I don't want to lug around close to 2,000 pennies. Okay, so how do you figure out the least number of coins and bills to specify the same number? Most people can do this without using a piece of paper to help, right? You just go like, oh, this is easy. I'll give you a $10 and then a $5 bill and then three $1 bills and then a single quarter. That's it, right? If you know how to do this already, was I wrong? Yeah. Huh? We'll pretend that $2 bills and half dollars do not exist, especially the half dollar thing, because they're really kind of rare and it looks like a quarter. It's thicker, but it still looks like a quarter. So we'll just pretend that $2 bills do not exist because they're kind of rare. All right. So if you can do this already, you have already practiced a skill to do way more than just base conversion. Okay. So let's change this up a little bit so that I can show you why you already know about base conversion. It's just that you don't know it yet. In other words, I know something about you that you think you do not know about yourself. Now, how cool is that, right? All right. So let's take a look at the usual US currency. Okay. We have a penny, which is a zero point zero 0.01 of a dollar. We have a nickel, which is zero point zero 0.05 of a dollar. We have a dime, which is zero point 0.1 of a dollar. We have quarters, which is 0.25 of a dollar. And remember, I said skipping the half dollar coins, so we're going to skip it. And then we have $1 bills, $5 bills. Then we have $10 bills, $20 bills, and $50 bills, and $100 bills. Is there any regularity in the multiplier to get to the next denomination? There's absolutely no pattern whatsoever. Okay? There's nothing recurring at all. Because to get from a penny to a nickel, times 5. To get from a nickel to a dime, times 2. To go from a dime to a quarter, times 4. Okay? So right here, There's no repetition whatsoever, right? So now we go from a 0.25 to a 1. It is a 4, right? You go like, hmm, okay. So up to this point, there's no repetition. And then we go from 1 to 5 again. You go like, oh, okay, this is a repetition pattern. Cool. Okay, that looks good. Not so good. So there's no actually recurring pattern whatsoever. Okay, it repeats a little bit, and then it doesn't repeat anymore, and then it repeats a little bit more, and then it doesn't repeat anymore. Okay, and yet you can wrap your mind around this and be able to give me the least number of coins and bills. Okay, so let me propose. Okay, if I were a politician, this would be my platform. Phase two. Okay, so the first thing I'm going to do, if I were the next presidential candidate, my platform is to change the US currency so that we have quarters, we have half dollars, we have $1, $2, $4, $8, $16, $32, and so on. Okay. Now, you look at this and go like, that is really awkward, right? Because instead of the usual currency denomination, I'm going like, what? A quarter to a half dollar to a $1 to a two, four, 8, 16, and 32. But what is cool about this? Everything is just doubling. Okay, because to go from a 0.25 to a 5.5 times 2, from zero point 0.5 to 1 times 2, 1 to 2 times 2, and so on, right? Are we good so far? Are you guys starting to look at see the pattern? So, assuming that I do become the next US president, which I cannot because I wasn't born in the US, um, and this turns out to be the policy that I get implemented, okay, before I get assassinated. How would you make up $18.25 using this new structure of currency? Okay, so I can hear you guys already knowing how to do it. We need one $16 bill, but after that, I don't think we need an $8 bill. Won't need a $4 bill. We're gonna need one $2 bill, right? And then we have none of $1 bill, and we're gonna need none of the half-dollar coin, and we're gonna have one $quarter coin. Is that right? Okay. Well, congratulations. You just converted a value into a binary number. And of course, you guys go like, what? What binary number are we talking about? Well, let me make this clear, okay? So if I were to write this number, and there's a zero here, so if I were to write this number horizontally, it'll be 0, 1, 0, 0, 1, 0, 0, 1. Okay. In other words, this zero of the 32 becomes the leftmost digit, because it's the most significant digit, and then this one representing that we have one of a quarter of a dollar becomes the rightmost digit, which is the least significant digit. Then you go like, that doesn't look like a number to me. Well, what if I put a dot right here? Okay, so not only is it a binary number, it is a binary number that has a fractional part. So now the question is, what exactly are these digits representing? Okay, so what these digits are representing is how many of a particular power of 2 do I need? Okay, so I need, so let's start with the ones. Okay, so the 1 is here. Okay, how many ones do we need? Which is 2 to the power of 0. I need none of them. Okay. If you move to the left hand side, you are doubling. Okay. So now we are asking how many $2 bills do we need? We need one of those. How many $4 bills do we need? None. How many $8 bills do we need? None. How many $16 bills do we need? One. And how many $32 bills do we need? None. What about the right hand side of digit 0? This is what I call digit 0. I'll explain that later. So we have this point here. The point of the point, no pun intended, is to mark where is digit 0. Digit 0 is immediately to the left hand side of the point. So what is on the right hand side of the point then? On the right hand side of the point, now you have negative powers of 2. This is representing how many 2 to the power of negative 1 do we need? What is 2 to the power of negative 1? 1 half, right? Or zero point 0.5. And what about the 1 to the right hand side of this particular digit? What about this one over here? It is asking how many of 2 to the power of negative 2 do we need, which is a quarter. Are we understanding this notation? The position of each digit is telling us which power of 2 are we talking about. The value of the digit itself is telling us the quantity that we need for that particular power of 2. Are we good so far? We good? Is this new to you? Do you need this class to learn this? Or how much are you learning from this class? Well, let's take a look at the base 10 numbers. Are we all comfortable with base 10 numbers? Okay, nobody is opposing the use of base 10 numbers, which is something that you have been working with since what, elementary school? Okay, so we'll take a look at the base 10 number. Okay, so with the base 10 number, we're going to look at, let's say, 46.125. Okay, so in this case, I'm going to rewrite this number in a very ingenious way. It is 40 times plus 6 plus zero point 0.1 plus 0.02, oops, oh 02 plus 0.005. Am I wrong? I'm not wrong. Just go like, why do you want to expand a nice number into a bunch of numbers and then add all those numbers back? Well, because I need to do the next step. I can re-express 40 as 4 times 10. I can re-express 6 as 6 times 1. I can re-express zero point 0.1 as 1 times 1 zero point 0.1. I can re-express 0.02 to 2 times 0.01, and then I can re-express 0.005 as 5 times 0.001. Okay, tedious, yes, but am I wrong? I hope not. Okay, but do you see a pattern? What pattern are you seeing? These are base 10, but the pattern that you probably are seeing, but you may not know how to articulate, is we are now looking at a single integer times a power of 10. Is 10 a power of 10? Well, 10 is 10 to the power of 1. What about 1? Is 1 a power of 10? It is 10 to the power of 0, right? What about 0.1? 10 to the power of negative 1. 0.01? Negative 2. 0.001? Negative 3. So it has exactly the same pattern as what we just talked about. The only difference is what is the base of the power. So let's make it even more clear. So this is 4 times 10 to the I'm gonna borrow the caret symbol to means to the power of, even though in C++ it actually means something else. So this is this plus 6 times 10 to the power of 0 plus 1 times 10 to the power of negative 1 plus 2 times 10 to the power of negative 2 plus 5 times 10 to the power of negative 3. Are we good so far? Okay. So now we go back to the binary number that we were talking about. This is, oh, okay, we remember what this is, right? We have none of the 32, we have one of the 16, we have none of the 8, we have none of the 4, we have one of the 2, none of the 1, none of the point 0.5, and finally we have one of the 0.25. Okay, let me resize the screen a little bit here. Okay. And now we convert everything into powers of 2, right? So what is 32 as a power of 2? You should not need a calculator to do this. 2 to the power of what is, yep, there we go. It is 2 to the power of 5. Thank you. So that's that. That's 2 to the power of 4. That's 2 to the power of 3, right? And then we have 2 to the power of 2. And then we have 2 to the power of 1. I mean, by this time you guys already know, how to finish this whole thing, but I'm gonna finish it anyway, just so that it is complete. Okay, we have none of 2 to the power of -1, and finally we have 1 of 2 to the power of -2. All right. So if you compare this entire expression just in terms of the format with this expression in terms of the format, do you think they look a little bit similar? We are specifying with one, we are specifying how many of a particular power of 2 do we need. The other one is expressing how many of a power of 10 do we need. So that is the structure. Okay, we are trying to extract the structure looking at the two formats. So the only difference is really the base. One is looking at powers of 2, which means 2 is the base. The other one is looking at powers of 10, which means 10 is the base. So what you already know about reading a base 10 number, you just have to be more flexible in terms of thinking what value it is representing, and you can easily understand what a base 2 number is representing because the structure is exactly the same. Are we understanding the concepts at this point? And then the whole conversion process is the same concept too, except you're now asking how many whatever power of 2 you need. So let's go ahead and finish this. Okay, so we're going to re-express 46.125 as a base 2 number. Okay, we'll just kind of practice whether we can do that or not. Yes, question? Okay, all right, so we're looking at 46.125, but this time we want to use base 2 to represent it, which means we're looking at, oh, okay, we have all of these multipliers already. So we are really, except for 0.125, which we already know how to get to 1.125. So now we just start with 32. Do we need a 32 for 46 and 0.125? Okay, we need a 32. We also need we don't need a 16. Okay, and what else do we need? I think we need an 8, and then we need a 4, we need a 2, and we are done with the whole numbers. And then on the other side, we just need 0.125. Is that okay? I'm just re-expressing 46.125 as a sum of powers of 2. Are we good? Okay. So now the next step is to say, oh, okay, so we have a 1 here, and then we have none of the 16, 1 of the 8, 1 of the 4, 1 of the 2, none of the 1, and then we have a point. Remember, the point of the point is to mark where do we find digit 0, which is the digit telling us how many 2 to the power 0 do we need. So now we go to the negative powers of 2. We have none of the half, none of the quarter, and 1 of the eighths. So this is the base 2 representation of 46.125. Are we doing okay so far with the base conversion? Okay. So do you think base conversion, or we can only have base 2 and base 10? Or can we also have other bases too, even prime numbers, like base 7? We can indeed. Okay. So we'll take a look at some really odd cases here, like a base 7 number. Yep. So rational numbers can is doable with all bases because a rational number can be expressed as a fraction with an integer or natural number as the numerator and a natural number as a denominator. That's the definition of a rational number. So I think what you meant to ask is, depending on the base, are there cases where if you express the value in one base, you only need a finite number of digits, but in a different base, you will need an infinite number of digits because the digits are repeating? Is that kind of what you meant to ask or not? If a number is irrational, then it will need an infinite number of digits to represent, regardless of the base, assuming the base itself is a uh, counting number. In other words, if you use pi as the base, then the value of pi itself would just be 1. So we are excluding those cases where the base itself is the irrational number. All right. But there are cases where that actually makes sense. Okay. If you think about a year, okay, how do you measure a year? As in year, year. It's actually an irrational number because the rotation of the Earth, the self rotation of the Earth, and the amount of time to go around the sun, that ratio is an irrational number. And that's why we have to come up with all these awkward rules to approximate the irrational number. Every 4 year is a leap year, right? And what is the next rule? Then yeah, every 100 is not a leap anymore, and then every 400 is a leap again, okay, and so on. So we have all these kind of awkward rules because we are trying to use whole numbers or fractions of a whole number to represent a irrational number. Most numbers are irrational. Yep. All right. Cool. So let's go ahead and work with base 7 numbers. Okay, so this time I'm going to give you a base 7 number to begin with, and I want you to tell me what value it is representing. Okay, so we'll start with 435 as a base 7 number, and I want to know what is the base 10 representation of 435 as a base 7 number. So the first thing you need to know or remember or recall or read your notes about is, what are these digits representing? What is, okay, we'll pick the 3, okay? Let me highlight it and then we'll talk about what 3 is representing here. What do you think this digit is representing? To the power of to the power of 1. This is digit 1, okay? So the 5 is actually digit 0, okay? Because the 5 is representing the quantity of 7 to the power of 0. That's why it is called digit 0, okay? So the 5 is representing 5 times 7 to the power of 0. So the 3 is representing, oh, the next power of 7, we need 3 of those, which means we have 3 times 7 to the power of 1. What about the 4? The 4 is telling us that we need 4 of 7 to the power of, what is the power? 2. That's right. Okay. So that means, if you want to expand, the value it's representing, it would be 4 times 7. to the power of 2 plus 3 times 7 to the power of 1 plus 5 times 7 to the power of 0. Okay, so now we can actually work it out, right? It's 4 times 49 plus 3 times 7 and then plus 5. So now we have, let's see, this is going to be 196 plus 21 plus 5. And if we work out the actual math here, then we have a 2 over here and a 3 and a 2 here and also a 2 here. So it would be 222 in base 10. So if I don't put parentheses and then a number after that, by default, it is a base 10 number. If it is a base 2 number, then you would see a parentheses 2. If it's a base 7 number, you see parentheses 7. But base 10 is the default, so I don't bother to kind of talk about the base because by default, it is base 10. Okay, how can I double check that 222 is indeed represented by 435 as a base 7 number? You just reverse the process, okay? That's all you need to do. So you reverse the process, which means now we have a little lookup table. 49 is 2 to the power, 7 to the power of 2. 7 is 7 to the power of 1, and then 1 is 7 to the power of 0. So now you look at 222 and you divide it by 49. And the answer is, oh, I can see that I'm wrong already. No, no, we're good, we're good. Okay, so I'm good here. Okay, so do you guys know how to do long division without a calculator? All right, so let's do it. Okay, I don't mean it in a mean way, but I never thought that I would need to explain long division in a college class. But my colleagues are telling me that no, don't assume people know how to do long division by hand. Is that true, or am I worrying about something that I don't have to worry about? Okay, 222 divided by 49. Uh, so the closest you can get would be a 4 because a 5 would be close to 250. Okay, so you need a 4 here. So 4 times 9 is a 36. 4 times 4 is a 16. 16 plus a 3 is a 19, like that, right? And then you do a subtraction. 2 minus 6 is a 6 in base 10. You have a borrow of 1. So 2 minus 9 is 3. 3 minus 1 is a 2. And because you have a borrow here, so you have 2 minus 1, which is a 0. So you have 4 with a remainder of 26. Is that okay? How do we call these things? 222 is called the dividend. 49 is called the divisor. The 4 is our quotient. And then 26 is our remainder. Very good. Okay. So being able to name all the parts of a long division is also helpful. Okay. Because now we can identify all the different components of a long division. So you take the 26 and you go like, okay, how many 7 can we find in 26? This one is kind of, you have to brute force. You have to remember your multiplication table. There are no other ways to do this, okay? Multiplication table. 3 times 7 is a 21. 26 minus 21 has a remainder of 5, okay? So, technically speaking, we're done, okay? But if you want to push it one more time, we can do that. We just ask, what is 5 divided by 1 with a remainder of 0, right? So that's how we end up with 4, which is our digit 2, 3, which is our digit 1, and 5, which is our digit 0. we got our base 7 representation back. So we went one way and then we went back the other way, and they're consistent. So does it mean that this process is actually correct? Not entirely. I did not give you a rigorous proof of whether this is the correct process or not, but the chances of me making two separate mistakes and somehow the two separate mistakes cancel out is really slim. It can happen, but it's not unlikely in this case. So are we doing okay so far in terms of doing the conversion both in both ways? You get all right. So in the other modules, we actually have to refer to mechanisms that are much more general. So what we do is we name the digits. Okay. So in this case, the 5 is a digit 0, the 3 is a digit 1, the 4 is a digit 2. So the way we express the value being represented is like this. Okay, so if you look up here, um, there are a few equations. So this equation is kind of useful. So in this equation, V is representing the value. The D's are representing individual digits. Okay, so D of 0 is digit 0, D of 1 is digit 1, D of 2 is digit 2, and so on. And it can go negative 2 because you have D of negative 1 being the number of whatever base to the power of negative 1. Okay, so this is how we can generalize and go like, whatever the base you're dealing with, as long as the base is a constant B, just stick it here. Okay, and then the D of i's are the individual digits of the number. V is the value represented by the number. So this immediately pops up a new question. Okay, what is the difference between a value and a number? It it's not just the base. One is the representation of the other one. Okay, so one is a way to convey a concept so that other people can understand. The other one is the thing being represented. Okay, let me give you an example. I'm holding up some fingers. Okay, and I want you to think in your head how to convey this concept to another person. Okay, so Cantonese is my native tongue, so I'm gonna say Sam, okay, because that is the Cantonese word to represent this quantity. Does anyone speak Spanish? Okay, what is this? Okay, how about Russian? Okay, how about okay, what other language do you guys speak? Farsi? Anyone? Yeah, go ahead. Okay. How about Farsi? Yeah. Okay, so that's the number, that's the representation. The concept is the value. This is V, okay? That's the value. This is what I want to represent. But all of those different words that we just heard are representations of that quantity. So that's the difference between a number, which is a representation, and the value, which is what we want to represent. So what we have also seen, in the examples just in this class is the same value can be represented in different bases. In other words, you can have an infinite number of representations for a single value. Is that okay? All right, so it's important to separate those two concepts, especially in this class, because otherwise the notes will be very confusing to read because I made a very clear distinction between what is V, which is the value that we want to represent, and the number, which is represented by the D of i's, which means each one is only representing a single digit of a number. So this is one useful equation. The other useful equation is down here. So this one is doing the opposite. If I give you a particular value, which is V, which is typically represented in base 10, because unless you know how to do division in other bases really easily, I would just stick with base 10. Okay, so B is usually represented as a base 10 number. B is the base that I want you to convert to. And we have already gone through an exercise with base 2. We have gone through another exercise with base 7. So B in this class, as an example, can be 2 or 7. I is indicating which digit we want to isolate. And this symbol here that looks like a square bracket missing the top is called the floor symbol. Okay, it's called a floor operation. The floor of a value is the largest integer that is less than or equal to whatever you're taking the floor of. So based on that, what is the floor of 2.9? In other words, 2, exactly. What is the floor of 2.1? What is the floor of negative 1.9? Hmm? Okay, so that's a tricky one. Okay, so once again, so people were not wrong when they wrote in ratemyprofessors.com that I like to trick people because I just threw a I just threw a tricky case. Okay, the floor of 1.9 is the largest integer that is less than or equal to 1.9. And what is it? It's negative 2. Very good. Okay, because it has to be less than or equal to. Negative 1 is not less than or equal to negative 1.9. Okay, so that's the trick. So why do you think I throw all kinds of tricky cases at you? It goes back to two concepts that we have talked about today. If I only throw like really easy cases for you to practice, okay, you guys can build up your self-confidence. It's like, oh, I can get to the answer. Cool. But when I throw tricky cases at you, you have to think about it a little bit, right? And what concepts have we talked about in today's lecture that relates to tricky cases? Critical thinking and problem solving. Okay? So it goes back to that. Okay? And if you just have to debug a program, what do you need to do when you debug a program? Is the error message? That's the starting point, right? The starting point is when you first notice the program is not doing what it is supposed to be doing. Okay? And then what do? You have to isolate the line of code that is the closest to the symptom. You know that at that point, the program is already not behaving correctly. And then you have to go backwards to figure out at which point of the program did something go wrong. What is the earliest point that, what is the earlier point of diversion from what the program is supposed to do? And that's going to take, guess what? Critical thinking and problem solving skills. So if you have been debugging your own program in CISP 360, then you have been practicing these two skills already. Unfortunately, many people do not have opportunities to practice that anymore. And why do you think that is the case? It also relates to something that I showed you in today's class. ChatGPT can debug your programs. You can give it a program that is buggy and ask ChatGPT. You can tell ChatGPT what it is supposed to do. And ChatGPT can actually debug the program for you. It will tell you what's wrong with it, why that mistake leads to the symptom, and how to fix it. Okay? It can do it already. So what you need to do, okay? So this is what I tell people, and I know it's a little bit depressing, is for you have about 2 to 3 years to figure out what you can do that AI in 2 years cannot do. Okay? Because that would be the reasons why a company wants to hire you. But since you know it now, okay, compared to people who do not yet know that, you still have a head start. So think of it that way. There's always a silver lining in everything because now you know what you need to learn in order to have the skill set to get hired. So I'm going to give you the lab of today. It's called NAN2. This is the lab for today, and it has a companion submission thing, just like last time. So I'm going to turn that on too. So both of these are what you need, and don't leave just yet, okay? Because you need an access code. So the access code is Nandroid. So it's like Android, but with an N in front of it. And Nandroid. And I will probably give you guys back more time, because I'm ending the lecture a little bit late, but I won't charge you extra for the extra time. And I don't have a link for tips either. So, all right. So I will see you guys over at the lab. You don't need to register again, so you can go to the lab and start working on the lab right away. And I'll be there in just a moment.